Hi, and welcome to an exciting edition of CG Game Development Programming. My name is Nate Nestler, and this is for Hyperactive Studios. Now, what we're getting ready to go over is normal mapping, and a bit of height mapping too, which gets into bump mapping, but also parallax mapping, and along with relief mapping. So lots of topics, and we'll have a look at this real quick. What does normal mapping look like, and what does it do? Well, you know how this model has been smooth previously, but we sit there and put this normal map on here, and the geometry hasn't changed, but it sure does look like it's now bumpier by far. We get all these wonderful details that seem to be appearing here, carved right into the side of the character's head. Now, I can come in here and manipulate these, and bang, it's gone. So, essentially, you can see the effect of the normal map on the surface here of the model as I move this. And this is what the normal map does. It allows us to create details that react to the lighting based off of images that are based off of highly detailed models that were made elsewhere. So, and then these maps were computed with their normals, which would be XYZ vector. These translated into an RGB color value. And of course, this doesn't map exactly because we can have negative and positive normals, and we'll get into that in just a second here. But we do have some variations here. All right, so let's also look at, you can also have it with reflections. So there we are with reflections here for our normal map, and it's super cool looking. And so as you can see, it really adds a lot of detail. It makes a night and day difference to this whole setup here. And then the other one we could look at is occlusion culling. Parallax mapping. It is 6:51 a.m. and I'm tired. Brain's partially here right now. But I can still do this anyways. Alright, so let's say open here. I'm just waiting for this to open up. And here we are. So right now I'm trying to see which one did I have it set to. I forget. Yeah, and this is based off their 2005 paper here. Here's our author of it. He invented this along with Oliver. I can't say his name. I'll say it wrong. I don't want to mispronounce his name because they did some amazing work. So right now I'm having it set to relief mapping. Now, relief mapping is really cool. This is a great representation. Look how sharp these edges and points are that occur from it. Now, this plane is nothing but flat. If I right click this and I say scene properties, I think it is. No, it's not. Okay, I can't remember what the magical click is anymore. But essentially, if I come in here and we were to look at this thing, it's nothing more than a flat plane. Now I know it doesn't look like a flat plane at all, but it actually is indeed a flat plane. If I take my just standard material to it, check it out, it is a flat plane. But once I apply relief mapping to it, it suddenly looks like it's got a whole lot of depth and a whole lot of stuff going on. So this is more advanced than normal mapping or even parallax mapping. Oh, sorry, that's the exponent. Sorry, I need to place the depth right. So you see, it looks like we're just suddenly manipulating the height of this thing. And it's a trick of camera distortion along with its self-occlusion and self-shadowing. And then basically it's warping the image pixels based on texture space. I just finished reading a good bit of the dissertation, doctoral dissertation from I believe it is Manuel's from Manuel here. He has his dissertation up here. If you go to this is not for the faint of heart, mind you. It's really quite complicated, so it's not something you would probably really want to read his dissertation unless you are the more adventurous type, but it is a very good dissertation. It's very nice. It's got a lot of cool information in it. Here is the lighter version here for you to read through stuff if you want to just read through his relief mapping techniques that he did his dissertation off of. And then of particular interest, this is actually the method we're going to be manipulating and working with, is the 2005 approach to their here it is, real-time relief mapping on arbitrary polygon surfaces. That one's really cool, and that's what we're using. That's what I'm showing off right now. But then they also went a step further and did another paper that, I don't know, maybe at some point in time we might implement, would be relief mapping on non-height field surface details. And this thing is awesome. Really cool white paper. Oh my gosh. Both of them are really cool, but this one's like, both of them are awesome. But we'll play around with this stuff. We'll try to work up in bits here. Here's an example of more relief mapping with an actual map here with this height map fields created. And here's an example of displacement mapping, which is just off of just a black and white image, and that's why you don't get a lot of stuff going on there. That's something else entirely. And then we'll get in here to also how to reconstruct. This is another good paper. This is by David Eberly, reconstructing a height field from a normal map. Now we're just going to do a generalized formula of it, but he's really got quite a bit going on in here. So if you're interested in these white papers, feel free to hit these up and hunt them down. And you know, some of them cost money. If you need to join ACM or IEEE, and that's ACM is Advanced Computing Machinery. Association of Computing Machinery. And that's ACM. A is in apple, C is in cat, M is machine. And that is a really wonderful resource. It really lets you get a lot of white papers for well, once you pay the money, free. If you're a student, it's really cheap. If you're a professional, it costs a good bit more money, but it's definitely well worth it. All right. So, real quick here, assuming I don't get things mixed up. Oh yeah, I wanted to point out his website. So his website's right up here, and it's inf.ufrgs.br/tilde, which is a little squiggle right here, right? And then OLIVEIRA/RTM, all caps, has to be all caps, .html, and that will take you to his page. And he's got all kinds of awesome stuff up there. At the time of this recording, I was really hoping for it, but the samples here for the video and demo and stuff, well, they come from, where is his name? Yeah, Fabio's website here, and his website's down right now. So if I go over here and I click on this currently, yeah, it's down. So hopefully when you go to it, it's up again, and this link is good, but for right now, it's not. It's gone. I don't know what happened, but it's gone. And it's really too bad. So I'd love to get my hands on that. Material. I love their work. Their work is amazing. They're brilliant people. All these guys doing this stuff, that are creating these documents, are just insanely intelligent. I mean, they're just, oh my gosh. All right. So anyway, there's all that information as far as that goes. Okay, so let's look at a breakdown on this. And also, this is a real quickie here. Example of a binormal, and I want to point out something. I don't know if I remember to write it up or not. Here's another example of not having the normal map and having a normal map. And here's a high resolution mesh. So the way these normal maps are created is that they actually take the low resolution mesh and line it up with the high resolution mesh here, and then they find the difference in the heights between the parts and then calculate the normals of the high resolution mesh as it varies according to the low resolution mesh and how they differ. And then based off of that, you want to do it in tangent space so that it generates it. Yes, there's lots of other spaces. There's camera space, object space, world space. And then there's tangent space. And the best one out of them all is tangent space. Tangent space is the only one that will allow you to do animation directly on, say you have a deformable character. Any character that runs around moves, right? It's going to have deforming mesh because the bones are going to move the points and stuff like that in the mesh in order to make it move around. Unless it's a daggone robot, that's going to be the case. Okay, so if that's happening and you got these normal maps, you get all these details on the character, and you start deforming the mesh to make it move around, your normal map's going to go nuts. It's going to flip out. It's going to be swimming through the normal map. So, it's not going to work. I don't know what to say. I mean, there are some special cases where you can code it and blah, blah, blah to make it work specifically for this. Man, forget it. You're going to write a normal map shader. You're going to have it in your game engine, and you're just going to use it over and over again for umpteen different models. And there's going to be thousands of models, and you're not going to code out a daggone normal map per one. Not to mention, you can't even reuse and reload the shader. Right, so instead of being able to reuse the shader throughout umpteen different models throughout the game, and that really matters too, mind you, because some of these consoles only allow for like 8 different shaders on it, at once loaded into it because they have such a minimalized memory. So if you're running with minimal memory and you only have a choice of 8 shaders, the last thing you're going to do is write a whole bunch of custom tangent-based, a whole bunch of normal-based shaders and stuff like that. And on a computer, you can get away with a lot more than you can on consoles, but on some of the consoles, man, you can't do more than about 8 shaders. So currently, at this time of this recording, so it's a good idea to not just waste a whole bunch of computations. Anyways, we'll talk about binormals. Binormals or bitangents, they are not the same thing. So, another example of a height map, as it's like, so you got this grayscale in black here, and you can have it to do displacement, like I was showing a second ago. Okay, and then I should have one on, well, this is tangent space. Okay, so this is a good point here, explain it. Alright, so you have a point on the surface here and coming off of there, and you can see your tangent space accordingly. It's tangent from the curve on the surface. And depending on if it's a curve or a surface, depends on whether or not it's a bitangent or a binormal. And hopefully I did the write-up on that. If I didn't, I need to go back and add that. Hold on a second. And this is, which one is this? This is normal distribution. That's not what I want. Surface normal-ish. Yeah, that's what happens with surface normals. As you can see, it comes off these different points like this. For every vertex, and your normal points off in that way. And so with the normal map, that's what it's doing per pixel. So it's actually given the normal direction for how the light should interact with the surface per pixel. That's how we fake it, because you have that high detail models normals, and they all point off in the direction for defining the curvature for the light. So basically the idea was, for this, was that, hey, let's just take all those normals from the high detail surface and let's make it into an image, so that way we can call it back and fake it out. And so that way when they have this low detailed model, the light source isn't going to know the difference, right? So when we do the light calculations, it's going to do the calculations based off the normals from that normal map, which would be those high detailed normals, and not the normals on the actual low detailed surface, right? So when we do that, it comes back looking really detailed on the surface when it's not actually really detailed. And that's how we're getting all this detail on the surface that isn't there. That's what's going on, It's sitting there reading these normals in and such. In this case, we also have self-shadowing and height map to do it for this relief mapping. But that's what's going on. That's how we're able to get all these extra details that wouldn't normally be there. Let me break out the parallax distortion here real quick. And show this off. And I'll do my own variation of this thing. We go to record a video, so everything's straightforward, because they got multiple techniques within this one file, and that's too complicated for people that are first learning this stuff. Alright, so here is our occlusion, not occlusion culling, but parallax mapping. So here's our parallax mapping. And thankfully this parallax mapping is very well done. We are not getting a telltale sign of a lot of parallax mapping is that the surface will look like it's running off the plane here, or off the screen, as it just melts off the side here. And it's not a good thing, but that happens all too often. So, in order to avoid this, we're not doing steep parallax mapping. We're not going to cover steep parallax mapping, nor will I ever. Reason why, I have implemented it in the past, and the reason why I'm not going to touch it or cover it is because of when I put it this thing at an extreme angle like this, it's going to look like the whole scene or the whole image is going to melt down the side of this polygon here, and it's going to look terrible. So you can't have it at any kind of extreme angle like this from the camera, because otherwise the effect is completely utterly destroyed, and it's just really not that useful. It's only good if you're at a real distance from it or something like that, or you're at a point where you're like this kind of to it, or maybe slight angle, but that's about it. You don't want to have like an extreme angle, because if you do, it tends to melt in a bad way. So in the case of parallax distortions here for parallax mapping, you really just don't want to be more than just a little bit of variation here in your angles. You don't want to have any kind of extreme angle. So right here it's already lost for the effect. About here to here is good. Not even there. About there to there is good. So you see your range of motion isn't that much for your camera before the effect starts getting destroyed. So be aware of that. Although this is better than just regular normal maps, so this is more detailed than that. So be aware of that. But it is cool, and this technique's been really well implemented, because like I said, a lot of times when I see parallax mapping, it does actually melt across this plane. So there's also one called iterative mapping, which is another variation on parallax mapping that can be done that will allow to avoid the smearing as much, and tends to retain more of the details closer to what relief mapping does. However, I found relief mapping to be the best and highest quality of them all. So that's my favorite one. It wins the cake. It takes the cake. It wins. Whatever. Okay. So here's a normals going on surface. And this is a double-sided normal. You'd have two different normals, and they're coming from the same point, typically. And that would be the way it go. And here they're showing that a normal plane going across this curvature surface. Of course, if you're going to have a real curvature surface like this and actually have it represented properly with lighting, you have to have lots of normals to represent that curve. That is why we're doing these all these details of this normals going across a very low poly surface, where your low poly would be like this, but you have this curvature like this. But to the surface, you have the normals that are bowing like this instead of being flat like this. So when the light hits it, it looks like this curved surface instead of this flat surface like this. And that's basically what's going on there. Alright. Did tangent space. Got too many of these open, right? Sounds like me. Alrighty. Ah, yes. So, and then here's a good example of it. Okay. So normal, tangent, and could be either binormal or bitangent depending on the circumstance. In this case, it's binormal, so we have an actual surface. You can see how this orients. So it's like as you imagine. Actually lays out and creates a whole new coordinate system of three-dimensional vectors here for creating it. And based off of this, we can actually determine our normals for our surface for how we're going to do our normal maps and things of this nature. So let's have a look at this. First off, how do we convert normals that are XYZ into RGB format? And considering that, you gotta realize your normals can be what? If it's just a normalized normal, your normalized normal, it's just direction. And of course, that's all we care about. We don't care about the magnitude for this. So when we're looking at this stuff, we're only interested in the direction, because that's all that matters for the light. We don't care about what the magnitude of the vector was. So these are all going to be normalized normals. But your normalized normal is going to be having a range of -1 to 1, right? +1 there. And so, of course, your texture space only goes what? 0 to 1. So that's a bit of a problem. Doesn't exactly fit. And then the other thing is we only have room for, well, X, Y, Z. And then what about our good old depth map? In the case of the relief mapping here, check out this. We got all this depth map. Now I said we had to have that earlier, right? Well, that's that grayscaled image for that depth map. So how do we get that? Sorry. How do we get that into our relief map? I mean, into our, well, yeah, if you want to call it that, into your normal map, so that way you have your depth map also. So you could have it as a separate map, you could have it as a separate map. That would be a problem. And the reason why is because really you only need, it's a grayscale image, right? It's black and white with grays in between. Okay, cool. Well, it doesn't take RGB to represent that. It only takes one float value for grayscale. You know, just how gray is it? Is it full gray all the way up to white? Or is it like no gray at all to all the way down to black? You know, that's it. And so you're only talking about one float value. Well, check it out. This means you can squeeze two sets of image maps into a single one and take advantage of the wonderful memory saving architecture space within inside the 3D cards. So essentially, we can do red for X, green for Y, and blue for Z. And then we can also do, for our alpha map, we can hold alpha for our grayscale image, which is going to be our height map. So with this, we can actually represent, if you're just doing regular normal map, it'll just be RGB. But if you're also going to be doing your height map, it's going to be RGBA, where A is going to be your alpha. Instead of being transparency like it normally is, you're going to read those values in from transparency and actually make that as a height map to drive your whole shader here, for in the case of relief shader. And so, you know, that really conserves and saves a lot of space. And artists can do that inside of Photoshop or GIMP. I'll probably go over how to do that when we get to relief mapping, how to actually create that. In the Blender series, I think I've already gone over how to create a normal map, so that's nothing new there. But so I actually got how to do that in there. But I can also go over how to create a height map for people who are interested. And it's pretty cool. And then once you take the height map out, then you need to put it into the alpha channel and paste it in there in either Photoshop or GIMP, either one, and save it out as a DDS file. Okay, so here's something we need to do. First off, though, we talked about what we have a problem with. We have a problem with, well, hey, our normal vectors don't fit within the space. Well, that's a bit of a problem, right? Because we need to go from -1 to 1 for our normals, but we only have to work with 0 to 1. So we are going to lose a little bit of precision, but it's very little precision. It's not enough to lose sleep over by any stretch of the imagination by doing this, but it's going to look amazing and good. The problem is that artists have to make sure they save it in an image format that's not going to lose too much color information. So if they do a very lossy format like JPEG or something like that, you're going to lose a lot of color information because it optimizes on the grayscale, which is fine if you're doing grayscale, but it's not fine for colors, because the colors, remember, the accuracy of the normal is based on that color information. So if it, you know, overly downgrades and samples out the color to where it doesn't use as much information, then you just lost a whole bunch of normal information that you need in order to do the normal map, and that's not going to work. So it has to maintain as much of the color channel as possible of the original calculations, or otherwise, when it does its compression algorithm on the actual texture, you will lose a tremendous amount of data that would actually make up your actual normals, and so then your normals become incredibly inaccurate, and you'll just get the worst results ever. So DDS format, Targa format, it's a good one too. And then I'm trying to think, what was the other one? It'll come to me. Targa, DDS, which is your your DXTs 1 through 5. And then you also have the possibility of another format that I use all the time, and now I can't think of what it's called. PNG. PNG is another one that you can use. So either PNG, Targa, or DDS are about the only formats I would take into consideration. Yes, there's TIFF, but it's uncompressed, so it's going to be huge. So you do want some compression just so it's not freaking huge. But anyways, let's look at how to convert this so that way it fits within our ranges that we're looking for. Alright. So if you think about it mathematically, and say we were to divide our algorithm, our number of our values. So let's take our extreme ranges here first, okay? So what we have one that's way too small, and you know, the -1 here, and as our smallest value, and our 1 over here that's 1 for our highest value. So we need to remap this as 0 to 1. Now let's face it, if we can get the extremes on each side of the scale to come out properly back into the extremes of this range here, then we've done it, mathematically speaking. Because everything else is going to fall in between these values and we're good to go. You know, who cares? It won't be a problem. So basically, let's focus on the extremes for these values here, for each one of these, for remapping these extremes from one algorithm to another. It's mathematics. So if we take -1, let's start with -1. So we take -1 here and we divide it by 2, we'll get -0.5. See, and that's what -1/2 here is. And then if I say -0.5 plus 0.5, guess what I get? I get 0. Okay, so that worked for -1 for getting rid of it and making it 0. Let's see if that works for a +1 too, though. This has got to work for both. Same algorithm has to work for both. Okay, because you can't change the algorithm. It's got to be the same algorithm. Works on one, has to work on the other, because it's got to work across all points on the actual normals here. So let's have a look at that for setting its range here. Remember, this would be actually computed per component too. So you're going to do it for X, Y, and Z of your normal in order to remap it into red, green, and blue. Alright, so if I take 1/2 of 1, I get 1/2. And if I say 0.5 plus 0.5, guess what I get? 1/0. So go from 1/0 to 1/0. So perfect. I have mapped this one here, remapped it as this here. Now obviously you're going to lose 0.002 precision on this, or I'm sorry, 0.001 precision. So you're going to lose 1/1000th of a point precision. That's it. That's all you're going to lose. It's not much. It's definitely not going to throw off the look. And that's why all that matters in the end is the look, and it's not going to make it look any different when it comes down to the end. It's too small of a variation to matter. So, you know, who cares? Thus remapping, okay, so yeah, so thus we've remapped -1, 1 to 0, 1. And the final algorithm below, below with acceptable precision loss. Like I said, acceptable precision loss here. So if you take your normal value, divide by 2, and then add 5 here to it, then we can get to we can assign this to our color value. And mind you, this is going to be XYZ here getting reassigned as RGB over here. Okay, so be aware of that. Okay, so now what happens if we want to convert? Now we've made an actual RGB image map. Cool. That holds normals. Now how do we get those normals back out of the RGB map? Just realize, what format is it in now? Well, now it's in the 0 to 1 format here, and we need it to come back as -1 to 1. Otherwise our normals are wrong. Well, gee, we're going to have to do something about that, right? So we're going to have to take and use a mathematical algorithm to convert it back to the range it's supposed to be. So we need to go from what? Our extremes again. Gotta hit our extremes. So we need to go from 0 to -1, and we need to go from 1 to 1 again. So it's pretty simple, really. I'm going to take 0, I'm going to subtract it from 0.5. It's going to give me -5, and then I'm going to multiply it times 2. So notice something. I'm just taking this algorithm here, instead of dividing by 2, I'm just reversing it, right? I'm multiplying it times 2. Instead of like adding 0.5 to it, I'm going to subtract 0.5. But I got to subtract 0.5 first in order to make this work. So I'm going to subtract 0.5 from it first. It'll give me -0.5, and then I'll multiply it times 2, and it'll give me -1. So check it out. I just went from 0 to -1 for my low end of my range. 0 to -1 here, okay? But now the same mathematical algorithm has to hold true from going from 1 to 1. So we have to end up with the exact same value it started with. So let's see if this holds up. So if I take 1.0, subtract it from 0.5, I get what? 0.5. Awesome. If I take 0.5 then and then multiply it times 2, what do I get? I get 1.0. So we're back to the beginning again. Great. So 1.0 remaps to 1.0. So great. Our algorithm came true for both points here, for our low and high, for our remapping here. And so it works now. That's great. So that works for all points. So now we have a way of going from a range of -1 to 1 and remapping all our normals directions, right? Because it's a unit vector, it's a normalized vector, and we're going to remap that to 0, 1, and then once it's 0, 1 inside the RGB colors there, inside the image map, we can read back the RGB as XYZ within the range of -1 to 1 instead of 0 to 1. So we still have that vector pointing to the proper direction in negative direction away from the camera or whatever, which is really important. It does need to be pointing away in world space coordinates or tangent space coordinates, probably tangent space. Could also be referred to as texture space, because as you saw before, the tangents go about that angle there. All right. So let's look at a few other things. All right, so this is fairly straightforward for this next part here. So tangent is a vector and angles itself with a curve. Yeah, okay, so yeah, it's based off the angle of a curve, covered in the derivative math series videos. Yeah, so we already went over what tangent is, mathematical. That is covered back in the math series. So please do check that out. It's partial derivatives with tangents and stuff like that in derivatives. And I go over this, and that's basically a derivative is how you find a tangent to a curve. And that is what a derivative is. And that's what this vector is. It's just a vector coming off of that curve like this, And so, of course, it's most accurate at the point at which it comes from. As it moves away from that point, it becomes less and less accurate. Bam, there you go. So you can see as it, as you update per point on the curve, more and more accurate your tangent becomes. This is a great representation of animated and everything. This is awesome. Alrighty. Normal. We already know what a normal is too. It's an upward vector that is perpendicular to the other two axes on the surface or a point. And typically this is x and y that are crossed in order to, by saying crossed, I mean cross product, okay? Same thing. Commonly it's referred in mathematics to being crossed. You cross one vector with another, you're talking about cross product. In order to get the 90-degree vector to both x and y, because it has to be 90 degrees to both, in order to come up with the resultant, which is the normal. In our case here, our normal is going to be 90 degrees to our binormal and our to our tangent. No, sorry, not bitangent. Okay, so typically this is, yeah, okay, I already said that. So binormal is a cross product of the normal of a point or surface crossed with the tangent of a point or surface. Okay, so I looked back over it, and it is a bitangent on a surface. So it's a binormal on a curve. So we have the curves cross on a curve here. Let's see if I can point this out. Yeah, so like on this curve that's on the surface, but basically we're on the curve, okay? This will be a binormal. So you'll have normal, binormal, and tangent. If it's on an actual surface, like a curved surface or something of that nature, it's another scenario, in which case then it'll be a bitangent, because when you do this on the surface here like this, you'll end up with a tangent and a bitangent coming off of here, because you can have multiple tangents here coming off of this, because it's a surface, it's not just a curve. Whereas a curve here, let's see if I can show you. On a curve here, you can only have one tangent. See, this is tangent to the curve going this way. Whereas on the normal here, you can have a normal coming this way and then a binormal coming off of that way. In the case of the surface here, it's a different scenario. You have a normal coming straight up. You can only have one normal here. And then you'd have a tangent coming off that way and a tangent coming off of that way, for instance. And so you're going to have a bitangent and a tangent. So that's why it's a difference between the two. And that commonly gets mixed up where people think it's the same thing and it's not. So just a real quick clearing up that little misunderstanding that a lot of people seem to have here on this. And always good to keep it straight as to what's what. But anyways, FYI, there you go. All right. So B here is our binormal, and we're saying our binormal is cross of tangent with our normal. So if you cross your tangent and your normal vectors, then you get your binormal. And, you know, just as you expect, if you cross your tangent and your binormal vectors, you get your normal. And if you cross your normal and your bitangent vectors, you get your tangent. And this makes total sense. Just think about it. It's fairly straightforward, really. You know, it's written up everywhere. You'll find that all over the place, man. Everybody's got that one written up. And it makes sense. Look at it this way. Check it out. They're all 90 degrees from each other. This means if you cross one with the other, then you get this other one. If you cross this one with this one, you're going to get this one, right? Because it's 90 degrees to both. And if I cross this one with this one, I get this one. Makes sense? So no matter which way I cross it, since they're all 90 degrees from each other, since they're all up at right angles here, if I cross one with the other, I'm going to get the other. No matter which order I do it in, I'm going to get one that gets me the other one, so on and so forth. So whichever two are crossed is going to give me the other one I didn't do a mathematical operation with. It's that simple. So it's straightforward, and that's why that rule works for all those, like that. All right. We can also throw it into a matrix form for doing a translation for normal space. So a matrix form for translating from normal space into object space. You must have the values for the binormal, normal, and tangent in order for this to work. So we need to go from normal space over into object space because you do have to convert it back. In order to do that, it's real simple. Tx, ty, tz here for your tangents here. Then for your binormal x, binormal y, binormal z, and then your normal x, normal y, normal z. And there's your matrix. So there's your transform matrix for going from the different spaces. There you go. Multiply it times that, and bam, you get it into object space from your normal space. So pretty simple. One other algorithm we want to be aware of. Let's just cover it here real quick. So converting from a height field to a normal map. And this is by David Eberly, which I showed off earlier, reconstructing the height field from a normal map. If you remember right, let's see here, where's that paper at? Yeah, here it is. Reconstructing a height field from a normal map. So if you check out that paper, it goes over the gritty details of it. Okay, how does this work? This is a generalized form. This is not the detailed form that he has in his paper. It's pretty, okay, it's really close to his. It's just simplified version of it and a little bit more straightforward in English. Some of these formulas for just saying something simple can go like the entire page long, no joke. They really can. You start looking at doctoral thesis papers for the dissertations or some of these white papers. The math on these can really get super long, and you can end up being like, take up an entire line. I'm not kidding you, they can. So I'm going to try to simplify things as much as possible as we get through this stuff, so that way it's not a ridiculous point of mathematics you'd have to have in order just to understand something very basic that's written up in a very technical manner. You can take anything simple and make it complicated enough if you throw enough technical jargon in there. So I'm going to try to reduce the technical jargon here substantially, so that way things are more straightforward and clear. All right, so converting from a height field to a normal map. So David Eberly goes over this. So we have n here is our normal, which is the resulting normal in x, y, z. Height is the grayscale height map. All right, so remember, what's a grayscale height map look like, guys? Well, like that, actually, but it's not a very good representation. But yeah, that is one, actually. Yeah, that's relief mapping. That's great, but it's not what we're looking for. This stuff is awesome, but it's, again, not what we're looking for. Which is too bad, because this stuff is awesome. No, maybe I forgot to pull it back up again, huh? Oh, wait, no, here we go. Here's a good example. Here's a height map. And this is what it did to the surface here when I used it as displacement. But yeah, we have our grayscale going up to our white's going to be our highest point, black's going to be our lowest point, or not, basically nothing at all. It doesn't do anything to the surface. And all your variations in between is your grays. And depending on how white it is, depends on how high it is, basically. That's all there is to it. So that same image there made it do this to the geometry. That was just a flat plane before they applied it. Okay? So very cool. Let's look at how we do that. Let's go from converting our height map to a normal map. All right, so height is the grayscale height map pixel values here. Okay? And then height next is going to be a right-handed, and the reason why that works out, because if you think about how your texture space lays out, right, it's 0 to 1 like this. It's in a box, more or less. 0 to 1, and then you have your 1, 1 over here, right? So you're going to be going to the right always as you go to access your values, okay? Because it will come out into an actual box, just as a quickie here. Yeah, so this texture space here, 0 is going to be down here, 1, 1, and then 1, 1 would be this corner up here. There you go. That's it, man. That's how you access the textures for UVs. Okay? So knowing that, you're going to actually check your pixels to the right-hand side of your pixel that you're at as you move through this image until you get down to nothing at all. And then, you know, the ones above it. Because again, we're starting here at the bottom, so you're always looking at above and to the right. If that makes sense. So again, the pixel next to you be above for one pixel above it, and then the other one be pixel to the right of it. You know, so on and so forth as you work your way up through the image until you get to the very tip here and you got nothing to look at anymore. So it makes sense. Now you would calculate it that way. So that's what we're doing here. Height next is going to be your right hand side pixel there on the map, on your height map. And then height top is going to be your pixel above your current pixel you're sampling, okay? So, and we have to look at these surrounding pixels, because look at it. How are you going to determine your normal otherwise? It's not really a great way to determine your normal. Actually, nothing beats geometry. If you have actual physical geometry to create your normal, that's going to be the most accurate one by far. It always comes up the best results. These kind of look flattened because you can't get, you just can't get all the values you need, man. You really can't. So basically, we're going to look at our surrounding pixels and see what the color variation of them is in order to try to determine the angle at which that would be for the point on the surface for that normal. And we're basically trying to guess that that's what it's going to be mathematically speaking. So it comes out okay, but it doesn't match as nearly as good as actually calculating it from real geometry that has real normals that are really pointing in the exact direction. You're guaranteed to get the right result. This is an approximation, more or less, because you can't do much better than that. But essentially what we do here, now you can take this calculation at the bottom here, calculate this once, and then feed this back in, you know, as a separate line. So calculate this once, and then, you know, and then you can compute it each time for each of your X, Y, and Z, you know, axes here, instead of like having to do this individually. Because if you calculate this whole formula over and over again for each individual component of the XYZ normal, man, you just wasted a whole bunch of computations. So again, compute this line as its own separate formula up above, and then call back to this formula as a single, you know, variable name to divide it by that, and bam, you're knocking them out left and right quickly and easily. All right, so let's look at this. So you're gonna have the height here minus height next all over the square, and this is for x here, all over the square root of height minus height top here squared for the whole thing here, plus height here minus height next squared, and then plus 1 for that whole thing there. So, and then you're going to take the square root of that. So once you get this, and you just reuse this over and over again. So again, we're doing our evaluation saying, hey, how much variation, what kind of variation do we have from the top? And let's square that. And then what kind of height variation do we have for next to us? So what kind of variation do we get from that? Okay, and then let's add that, and then let's add 1 to get back to our original range here for values. And then, you know, you're basically taking that, and then you're going to take the square root of that to bring it half it back out again, more or less, by a power of 1/2. And then that's going to give you back to about where you want to be. And then you're going to say height minus height next here for x. Why x? Because it's going to be going in that direction to the right for that right value there. In the case of height top here, again, what is this one? RGB, right? Which is X, Y, Z. So height's going to be the top one. So, this is going to do our X going over to the right, pointing over to the right. It's going to be our X. Our green is going to be going up and down for Y. Okay, very cool. Wrong thing. And then Z is just going to be 1 over here because when you don't have a value for Z, it just ends up being 1. It's very typical. So with this, again, you're not going to get exact results. Like I said, you can only have 2. Let's face it. It's got X and Y. That's all it's got to work with. It doesn't even have the Z direction. So it ends up looking kind of off, flattened normal maps. But it does a decent job, like I said. But it's no replacement for actual real physical geometry. Alright, so we have 1 over here, and then same old down here. This doesn't change. Same exact calculation as before. So like I said, repeat this off as a separate one, and then come through here and calculate it as such. Alright, but with that, that pretty much goes over what we need for basic details on it here for, normal maps and height maps. And so that way we can do normals and parallax mapping and relief mapping. And remember, in the case of relief mapping and this parallax mapping, we're actually distorting, we're actually warping the actual pixels here on the screen in order to create these overlapping distortions or self-occlusion or or blocks. Part of the image blocks another part. It's actually skewing pixels around and manipulating. Skewing is a good word for it because that's what we're doing. We're actually skewing the pixels. I'm not going to get into a detailed discussion of that until we get into actual relief mapping. But I guess with that, that covers the subject matter here. So that goes over how the theory for normal mapping, relief mapping, parallax mapping, and bump mapping, along with displacement mapping. There's 5 mappings there. And that's how we go about it and how we convert things from one thing to another, etc., etc. But with that, my name is Nate Nestler, and this is for Hyperactive Studios.